Hello everyone. In this lecture, we will learn how insert operation works in AVL tree. As an overview, we will have a look at the initialization of AVL tree, implementation of insert operation in AVL tree, and implementation of rotations in AVL tree. First, to be able to implement an AVL tree, we need to have the structure which will be used to create AVL tree and its operation methods. As we know, every binary search tree has left and right pointer nodes which determines the address of the nodes that are connected to a node as left and right. Every node should have a key value which will be used to locate a node with data with specific key at binary search tree. Unlike in binary search tree, AVL tree has additional height value that is stored for each node. This is used to calculate balance factor and take required action if the calculated value is bigger than +1 or lesser than -1. So next, let's have a look at insert operation. We know from previous lectures that we have always used our data as our key value. So this is the case in this example as well. As method, we have insert with one input argument data and another call of that insert method with two input arguments which will be starting from root and the result will be equal to that root's node. As our starting value, we can insert key value of 40. First insert is quite simple since it will be our very first value to be inserted in AVL tree, but it's a good start as we will be adding more nodes in coming steps. As a start, we check if our root is null. It is null, so we basically say that root is equal to new node with data. If you remember how we have initialized our node at the previous slide, we had a default constructor that initializes the value of height as 0. So new node will have all the values as root node, data with null pointers, and height of 0. We returned and finished execution. As second value, let's add 33. Now root is not empty, so we skip next and check if the data is smaller than the root's data. It is smaller, so we will have our first recursion which will at the end return value for our root.left. We can store values before we get into next recursion in our method call. Next, we have another insert call with root, this time as root.left, and with data of 33. Our new root is now root.left, which is null. So this means our root is also null. We can see this by looking at the last method call, and also our previous recursion's input argument of root.left, which is now our new root at this recursion. So we create new node that will be taking data and height with left and right pointers that are null, and return root value to previous recursion which will be equal to root.left. So after returning from recursion, we have left the recursion at this method call in line number 6. In line number 6, root is 40. From previous method call, we have returned value of 33, which now will be root.left's value. So key value of 40 is left will be pointing now to 33. As you remember from our previous theoretical lecture, the height of a node is equal to number of edges from a specific node to the furthest descendant node. So now root node's furthest descendant node is 33, and there is one edge from 40 to 33. This means we need to update the height of our root node. So here let's take a moment and look at the logic of structure in insertion method. The constructor that has default height of 0 now makes sense since the latest added node will always have the height of 0. Another thing is the recursive approach. It gives very stable control over the creation of AVL tree as we already see here. This is because as we return from a recursion after a specific node is inserted, it will be updating the predecessor's node's height as it travels through that recursion. This is the same case to check up the balance factor after a height update. You may now have better understanding why recursions are sometimes very good solutions over the iterative approach. Even if when recursions give very simple solutions, some data structure models by their nature doesn't support recursive solutions. Though this is another day's topic. But now let's go on and continue with our insertion method. So here we update the root's height. To calculate height, we have a basic method that returns -1 from an input if the input is null and returns the height value of that input if it isn't null. Using max function returns basically the maximum value between two inputs. So root's height is equal to 1 plus the maximum height. So here we get the maximum value from the root.left and root.right. Root.left's height is 0. We know that because there is not with value of 33. But anyhow, the root.right has null pointer. From the height function, we know that it will return -1. As it returns -1, the maximum between 0 and -1 will return 0. 1 plus 0 is equal to 1. So this is one way to update the height of a node in practice. So now we have updated height of root, so we can check if the balance factor is in valid form. To check this, we can use a basic method again to find the balance factor. So as same as in theory, balance factor will return difference from height of left subtree and height of right subtree. This will return 1, because 0 minus -1 is equal to 1. As there is no violation, the next if statements will be skipped because balance factor neither equal to 2 nor -2. And as skipped over the cases, we return our roots. Next, let's add another node in our AVL tree with value of 24. Again, we go through same recursion until our recursive root is null and new node will be inserted. So here we update height with same formula and same logic. We calculate the balance factor. It doesn't violate the AVL tree at this point, so we skip to the coming statements. At this method call, we have left at line number 6, where return value was equal to 33 as root.left. At this method call, we have left at line number 6, where return value was equal to 33 as root.left. We update the height and calculate the balance factor. When we calculate the balance factor though, now you can see that left subtree has the height of 1 and right subtree is null, which will be equal to -1. So from the formula, 1 minus -1 will be equal to 2. So at this node, we have a violation, which will require a rotation. There are 4 cases and 2 rotation methods I have mentioned in previous lecture. You can see that the algorithm for 2 rotations can satisfy 4 cases to take required actions. There are a couple of ways we can determine the cases we are facing at this current state. The way that I show here is one way to determine which case do our violation fits. So if balance factor is 2, it means the left subtree is violating the balance factor. This was mentioned in previous lecture. There are 2 cases possible at this current state. We rather can have left-left case or left-right case, because 2 other cases are eliminated by knowing the value that returned from the balance factor, which is 2. To determine which one of 2 cases do our violation fits, we can check if the data is smaller than the root's left data. This ensures that the value is connected to predecessor's node's left pointer. This also ensures that we have a left-left case in this situation, because if data would be bigger than the predecessor's node's data, the predecessor's node's right pointer would point to the latest inserted data, or in other terms, key value. So yeah, basically we have left-left case. We need to do right rotation. To do right rotation, we can have inputs in a method to return the reformatted AVL tree. So in this method, we might have inputs as x and y, where the nodes which has to be rotated will be equal to those variables. In this visualization, you may see how the AVL tree would rotate when a specific rotation is made. As you can see, we don't either violate binary search definition or AVL tree definition by doing this rotation. So let's take this visualization and put it at the right corner to see how we will be satisfying our rotation case. So we have y, x inputs, and tree 1. Tree 1 here stands for the descendant nodes of the left subtree for the value x. As our tree 2 and tree 3 is null, you may imagine that there are null trees for those corresponding statements. So we do right rotation, and you can see that our rotations fits to our visualization given at the right corner. But how to do this practically? So let's have a look at it. So first we get our root as input for the right rotate. Our root will be our y argument. X will be equal to y.left, so key value of 33 will be our x. T2 in this case will be null, but our algorithm should work regardless of the value that is assigned to it. So we perform rotation here. X.right becomes as y, which is our root. Y.left becomes as our T2. We update heights of moved nodes, so node y will have height of 0 since maximum will return -1 and -1 plus 1 will return 0. And height of x will be +1 since maximum will return 0 and +1 will return +1 as height of x. And now we have all nodes connected to x, so we can return x as our new formatted AVL tree. We have returned with new formation, and we return same formation and finish the execution as we don't have any other method call left in our runtime. To see how right case is working in practice, let's add some nodes in our AVL tree. So same as previous insertions, we go through the AVL tree with recursion until we find a null pointer that is corresponding to the location of the new key value of 90. So we don't have any violation after updating the heights and calculating the balance factor. We go and insert 100 in our AVL tree. Again, traversing recursively and inserting the key value of 100 with a new node. So here we go through the method call and update heights and calculate the balance factor. At this method call though, we can all see now that we have a violation. So keep up and see how we deal with it. In this case, 40's height will be 2 since the maximum from root.left and root.right will return 1. So 1 plus 1 is equal to 2. So here the balance vector will return -2 because left subtree has the height of -1 and right subtree has the height of +1. -1 minus +1 is equal to -2. As we remember from theory, if we have -2 balance factor, it means that right subtree is violating the balancing, and now we need to determine which case our violation fits. To know if it fits right case, just like in previous violation where we had left case, we can determine the case by knowing if data is bigger than the root's right data. This will ensure that root's right data's right pointer will be pointing at the last insertion. So if this is the case, and which it is, it means we have right case where we need to perform left rotation. Again, we can have a look at our visualization and see how after left rotation from right to left, our AVL tree will be reformatted. Let's put the visualization at the right corner and follow the theorem as we perform the rotation. Now our X and Y is 40 and 90, and we perform left rotation. So this would be the result after our left rotation in our AVL tree. I want to mention once again, to not anything to confuse you, tree 1, tree 2 and tree 3 here shows the all descendant nodes for a specific subtree. This way, you will know how tree will be reallocated after the rotation. So again, we take input as our current root node, which is 40, and say that it is our X. We assign that Y will be equal to X.right, and T2 will be equal to Y.left. We perform rotation by assigning Y.left to X and X.right to T2. Here, I want to indicate that connection you see in the slide actually doesn't exist between node with key value of 33 and key value of 90. The connection of these nodes will be occurring after we return Y from this method and returning from that to the right of our 33 node. So after rotation, we need to recalculate new heights of rotated nodes. After recalculation, we basically return our fully merged Y node. And from this line, we return again same merged Y node as right of the root node. So here, as I have mentioned, the connection between 33 and 90 would be occurring as we assign as root.right of this current method call. So after fully connected AVL tree, we calculate the height of this node and finish as we don't have any other method call in our runtime. Next, I'll be showing you how we deal with left-right case situation in AVL tree. To speed up the process, as we already know how insertion works in AVL tree, I will simulate the insertion of node with key value of 95 in our AVL tree. So after simulation, let's go on and insert 97 in our AVL tree. Same as previous, I will slowly flow over the code and recursion until 97 is added in our AVL tree. So after returning from one method call, we know we have left at line number 8. We need to update the height of the current root and return as we will not have a violation at this state. As our new root 100, we have left at line number 6, which we have returned key value of node 95 as our root.left. So we can go to calculation of height from here on. The maximum of height will be returned as 1, and 1 plus 1 is 2. So in this current root, we get as our new height for this as 2. Get balance will return our balance factor, so 1 minus minus 1 will be equal to 2. This means the violation is at the left subtree, and now we need to determine whether we have left-left case or left-right case. Here, if data would be smaller than the root's left data, then we would be sure that it is left case. But the data is bigger than the root's left data, as 97 is bigger than 95. So we skip this if statement and go next. Balance factor is not -2, so we skip this statement as well and get to the next one. At this one, our balance factor is 2 and our data is bigger than the root's left data. This ensures that we have left-right case since data's predecessor node is pointing as right of data's node, or in other terms, key value of the node. In this case, we first make left rotation. Here, please pay attention, we take as our input not as root but as root.left, which will be node with value of 95. Because if you remember from previous lecture, we first rotate the root's left to left and connected node to the location of the root's left. So in this case, our x will be 95 and y will be 97. T2 is y.left. We perform rotations. Y.left becomes as x and x.right as T2. We update the heights of relocated nodes and return the merge node y as our new root.left. Next, we do right rotation, by this time taking the root node, but not the root.left. We perform rotation and recalculate the height of relocated nodes. And we return our x as our new merge node. Here in this call, root.right now connects node 90 to node 97. We recalculate the heights and return from this method call and finish. Now we have proven the theory in practice. I believe that you now have better understanding why we have two rotation methods but for cases. I didn't show you the right-left case. This is because it would be same as left-right case but with opposite operation sequence. You may go on and try to implement this approach on Java or any other object-oriented programming language and test by debugging the right-left case to see how it behaves when you have a right-left case scenario. At the next lecture, we will have a look at AVL tree deletion operation and how it is implemented in data structures. But for now, we finish here, so hope to see you in the next lecture.